In this tutorial, I'll be giving a sample problem on Newton's second law with kinematics. So for this problem, it says here, a bucket of water has a mass of 4.30 kilograms and is pulled upward by a cord with negligible mass. The breaking strength of the cord is 75.0 newtons. If the bucket starts from rest, what is the shortest time needed to lift it vertically through a distance of 15.0 meters without breaking the cord? So in case the problem does not make sense to you conceptually, it's basically asking us what is the fastest time that you should be pulling up this bucket of water so that the rope doesn't break. Because as you know, the speed at which you pull a rope or any one-dimensional object would determine whether it will snap or not, right? Besides the weight, of course, of the object. So that's the question there. What's the minimum amount of time that you should be lifting it so you don't break the cord? So how do we solve for this problem? Well, I think the best way to start solving, let's say you have no idea that this is Newton's second law in kinematics, we should write the given first. And then from there we analyze what should be done, what equation to use, etc. So for the given, the mass of the bucket with water is 4.30 kilograms. And then it says here that the breaking strength of the cord is 75.0 newtons. So we're gonna write it as T sub max equals 75.0 newtons. So the maximum tension force is 75.0 newtons. And then it says here, the bucket will be moving at a distance of 15.0 meters. So that will be the displacement along Y. Take note that this has a positive value because displacement is positive when the final position is higher than the initial position. And then the initial vertical velocity, or v naught y, is 0 meters per second because the bucket starts from rest. And then the required to find is time, obviously because it says here what's the shortest time needed to lift this bucket upward without breaking the cord. So in this case, what might come to our mind first is kinematics, right? Because the required to find is time, and then you see the other kinematic variables like displacement, velocity. So we can consider thinking of kinematics first. And if you look at the inventory of our y, or vertical variables, we actually know displacement. We also know initial vertical velocity, and then time is the required to find. And if you look at this, this is required to find. So if you look at this inventory of given variables, you can see that the missing variables are v sub y, or final vertical velocity, and then acceleration along y. So when you say mv, or missing variable, that's the term I use to describe a variable that is not known in the problem, but it's also not the one that we're solving for. Now take note that this is a stumbling block in solving the problem because if you look at our kinematic equations, they all require at least 3 known variables for them to be usable to us, or in other terms, they require you to have only 1 missing variable. But in this case, we have 2 missing variables. So whenever you are stuck in this kind of case, you need to find a way to determine the value of one of your 2 missing variables. So you only end up having 1 missing variable. And in this case, if you look at the other given, we have mass. We're also given a force. And because of that, you can actually determine the acceleration of the bucket by using Newton's second law, right? Miss, why did you say you need to use second law? Because you know how the problem really goes. I know, because the thing is that you need to look at the variables present in the problem. So again, if you have mass and then you also have force and then you have acceleration, then what is that equation that relates these variables? Of course, that is Newton's second law, which says that the net external force acting on an object is equal to the product of its mass and acceleration, right? So I just added the subscript y to indicate that this is in vertical motion. So by using Newton's second law, we can determine the acceleration, leaving us with just v sub y as our missing variable. So let's set that up. We divide both sides of the equation by mass, so that acceleration along y will be equal to the sum of forces along y divided by mass. And then take note, you might be tempted to use the given tension force here as the sigma f sub y, but that is not correct because sigma f sub y again is sum of the forces acting along y. So if you set up a free body diagram with this box representing the bucket of water, you have to imagine what are those forces acting on it. So first, obviously, whether the bucket has been lifted or not, there is gravitational pull acting on it, and that is called weight. So weight is the downfall pull of the earth, and weight is equivalent to mass times gravitational acceleration. And then apart from that, of course, there will be a tension force acting upward through the rope, and it will be a longer arrow because obviously you need to exert a tension force with higher magnitude than the weight of the bucket if you want to accelerate it upward. So those are the forces acting on the bucket of water. So in short, sigma F sub y, or sum of the forces along y, will be equal to the sum of the tension force and the weight of the bucket. Okay. And then take note, weight is equivalent to mg, or mass times gravitational acceleration. So we can replace w with mg in this expression. And then at this point, we can go back to our equation for acceleration. So this one, it will look like this. There's nothing bloody in here. I just replace sigma F sub y with tension plus mg because that is what it's equivalent to. Next, we plug in the given. So tension force is 75 newtons, and then this is the mass of the bucket. This is gravitational acceleration on Earth, and then this is again the mass of the bucket. Now take note that this solution makes sense because as you can see, the weight will end up becoming negative, and that makes sense because weight is pointing downward, so it has to really have a negative sign. Also, it will end up canceling or diminishing this tension force value because tension and weight are pointing in opposite directions. So tension is upward, weight is downward. Okay, and then take note, you might be wondering, Miss, why are we using 75 newtons for the tension force, or T? It says here it's the breaking strength, so it's just the maximum. When you say breaking strength, by the way, that's the maximum amount of force that you can exert on the cord so it doesn't break. But why can't we make it lower or what? So take note that it says here we have to determine the shortest time needed to lift the bucket, and if you want the shortest time to lift the bucket, then you have to max out or maximize this breaking strength of the cord. So you use the highest possible tension force and have it exerted on the rope for you to get that shortest time to lift the bucket upward, okay? Now, we can do the math for this in your calculator, but just to explain the units, take note that kilogram times meters per second squared is equivalent to Newton, and then Newton plus Newton in here will still give you Newton, but take note, Newton is equivalent to kilogram meters per second squared, and you'll end up canceling kilograms in here, so the final unit for the acceleration will be meters per second squared. So take note that this is easy, you just multiply 4.3 by 9.8 or negative 9.8 and then add it to here, divided by this. So this is our acceleration value now. So we can write it as a given, okay? So there you go, acceleration is 7.64 meters per second squared. It makes sense it came out as positive because it's actually going upward. I mean, it's accelerating upward due to the upward pull that you're giving the bucket and the rope system, bucket and rope system. What's the next thing that we're gonna do? So we can now go back to our kinematic solution, and we can see right now that we have d sub y, we have v naught y, and then we also have acceleration. And since we're solving for time, it shows here that the only missing variable we have left is v sub y. Again, missing variable is the one that you don't know in the problem, and it's also not the one that you're solving for. So with v sub y as our missing variable, the technique is to use an equation which does not contain v sub y, or final vertical velocity. I say again, when you pick a kinematic equation, you pick the equation that does not contain your missing variable. So in this case, we're gonna pick this last equation because it does not contain the missing variable, which is v sub y, okay? So let's write it down. So that's our chosen equation. Now take note that v naught y is actually 0. So you can cancel this entire expression, v naught y times time. We end up having d sub y equals a sub y t squared divided by 2. And then we cross multiply this because we want to have it written linearly so we can easily isolate time, which is the one that we're solving for. So and we end up having 2dy equals a sub y times squared. Next, we have to divide both sides of the equation by a sub y, so we can cancel it on the right side of the equation, leaving us behind with the required to find, which is times squared, although of course, definitely we still have to flip this horizontally because we're more used to seeing the required to find on the left side of the equation by convention. And eventually you have to cancel this exponent too, and to do that, you have to take the square root of both sides of the equation. And if you do that, of course, square root of time squared equals time. So you're going to end up having time equals square root of 2d sub y over a sub y, okay? The next thing is just plug and chug. So d sub y is 15.0 meters, and then the acceleration along y, as solved earlier, is 7.64 meters per second squared. And if you do this in your calculator, you're supposed to get 1.98 seconds. So that's our final answer in the problem. Okay, so the unit will be seconds because square root of s squared will be s. Now, at this point, you can actually stop watching the video if your goal is to really just know how to solve the problem. But you can continue watching if you want to have some additional conceptual insights, which might be important for you. So take note that this number, 1.98 seconds, it implies that this is the shortest time that you should be pulling the bucket upward. If you go faster than 2 seconds, that means to say that the cord is most probably gonna snap. However, in realistic scenarios, it's actually more practical to like spend a longer time pulling it up. So let's say, for example, maybe you would like to pull it within 2.5 seconds or 3 seconds instead, because that would be safer for the rope to not experience any tension higher than 75.0 newtons. And if you're looking for a justification, like, Miss, are you really sure I have to like prolong the time for the cord to be safer? Yes, that's true, because if you look at this, you remember we use 75.0 newtons because we want to like have the shortest time possible lifting the bucket upward. So like we max out the braking strength of the cord. But if you want to be like safer, let's say you're paranoid, I don't want to break the cord, maybe I should pull it slower. That makes sense. That the right strategy to like lessen the probability of breaking the cord or exceeding its braking strength is by increasing the amount of time that you're giving it an upward pull. And the mathematical justification for that is here. So let's say, for example, instead of 75 newtons, you just want the core to experience like 60 newtons tension force. So if you lower this, lower tension force would mean lower acceleration for the cord, right? Lower acceleration will happen if the time you spend pulling the cord upward is higher. So as you can see, in this equation, lower acceleration would mean higher time. So that means to say, if you want to have a safer scenario where it's less likely to go beyond the braking strength of the cord, which is 75.0 newtons, you would want to like prolong the amount of time that you are pulling it up. Okay, it doesn't mean that you need to find like a person who's weaker physically, because you might be wondering, Miss, what if I want to have like a weaker pull or a weaker tension force along the cord? What do I do? Do I find a weaker person to like pull the cord up? No, what you need to do is just to give it higher pulling time, because again, higher pulling time would mean less acceleration, and less acceleration on the system, on the bucket rope system, would mean less tension force will be acting along the cord. So that will be a safer scenario. And again, by common experience, you probably know that. Because if you want to break a piece of thread, for example, you actually snap it as quick as possible, because by experience, that's just how it works. And this is the physics behind that, okay? But if you are pulling something and you want to avoid breaking the cord, what you do is you pull the cord slowly for you to like avoid breaking it, right? So that's the physical interpretation of these numbers. That's all. I hope that you understood what the problem is, and thanks for watching.